Good morning, everyone. I am Bhushan Gopala Reddy, and today I'll be discussing our research on resilient health monitoring system, specifically engineered for disaster zones. The subtitle of my presentation captures our core mission: transforming proof of concept health monitoring into battle-tested system capable of operating when infrastructure fails. This is crucial work because traditional health monitoring systems are designed for controlled environment with reliable power and stable network connectivity, conditions that simply doesn't exist in disaster zones. When earthquakes strike, hurricane hits, or other catastrophe occur, conventional healthcare infrastructure collapses precisely when it's necessary most. Research addresses this challenge by reimagining health monitoring technology from the ground up, focusing on resilience, power efficiency, and reliable communication, even in the most challenging environment. The ultimate challenge. When designing the health monitoring for disaster zone, we face three critical challenges that form what I call the ultimate challenge. First, we need to provide life-critical monitoring. This means tracking vital signs including heart rate, blood oxygen level, SpO2, body temperature, and respiratory functions. Parameters that can mean the difference between life and death. Unlike consumer fitness trackers that can tolerate occasional inaccuracy, our system must maintain clinical accuracy even under extreme conditions. Second, we operate in hostile environment when traditional infrastructure has collapsed. Think about post-earthquake scenario. There is no power grid, no internet connectivity, extreme temperature, dust and debris. Our system must continue functioning reliably despite these conditions. Finally, we are targeting 99.99% uptime. This means our system can only afford about 5 minutes of downtime per year. When lights depend on continuous monitoring, this level of reliability isn't a luxury, it's an absolute necessary. The daily connection resilience. To meet these challenges, we have developed several innovations in BLE connection resilience. First, our dynamic device discovery enables automated reconnection protocols that continuously adapt to challenging environments. This means that as healthcare providers know patients or as condition changes, the system automatically rebuilds connections without requiring manual reconfiguration. We have implemented multi-path communication that ensures signal persistence even when primary route fails. Our field testing shows that approaches has increased connection reliability from 92.4% to 99.7%, a critical improvement when lives are at stake. The system includes sophisticated signal degradation handling that maintains core functionality even at minimal signal strength. Even at signal levels as low as minus 95 dBm, the system continues transmitting essential vital signs. Perhaps most importantly, our device from mesh network where they can rely on data when direct connection fails. This creates a self-seeding network architecture that can route around damaged or disconnected nodes, maintaining continuous monitoring capability despite localized failure. Power optimization breakthrough. Power management represents one of our most significant innovations as it directly impacts how long these systems can operate in the field. Our dynamic sensors sampling intelligently vary connection frequency based on the patient's criticality and remaining power reserves. For stable patient, sampling rate can decrease to conserve power when critical patients are monitoring more frequently. This approach had demonstrated as a remarkable 62.4% reduction in power consumption for stable patients while maintaining clinical standards. We have implemented advanced edge computing algorithm that analyzes data locally, drastically reducing energy-intensive transmission. This low-power processing approach has reduced idle current consumption from 4.2 milliamps to just 0.8 milliamps, an 81% improvement that directly translates to longer operational life. And transmission optimization uses strategic compression and scheduled data delivery protocols to reduce radioactivity cycle. By coordinating transmission windows across multiple devices, we have achieved a 28.3% reduction in overall power consumption as compared to standard BLE implementation. Finally, we have integrated innovative energy harvesting technology that captures kinetic, thermal, and ambient RF energy. These micro-generators create self-sustained power systems that can extend operational duration by 18 to 26% under favorable conditions, potentially providing indefinite operation in some field settings. OTA update in constrained networks. Maintaining software currently is vital for security and functionality, but traditional update mechanism fails in disaster environment with limited connectivity. Our Delta update approach translates only modified components rather than complete firmware images. This reduces bandwidth demand by over 80%. With typical update payload size dropping from 48 to 96 KB to just 8 to 12 KB, this efficiency is critical where the network resources are severely constrained. We have developed proprietary extreme compression algorithm that can shrink update payloads by nearly 83%. This enables critical patches even on severely limited networks where traditional update would be impossible. Our partial update recovery uses sophisticated checkpointing to allow interrupted updates to resume from the breakpoints. This eliminates redundancy data transfer during network fluctuation, ensuring updates are complete even with intermittent connectivity. Finally, our intelligent rollback safety mechanism automatically reverts to the last stable version if deployment integrity check fails. This ensures continuous device operation even when updates encounter problems, with field testing demonstrated a 92.2% first attempt update success rate. Next, let's talk about distributed observability. Maintaining visibility into the system performance is crucial in disaster scenarios, but traditional monitoring approach fails without reliable infrastructure. Our system provides comprehensive real-time visualization across all deployed monitoring devices in the disaster zones. This gives emergency responders and medical personnel immediate insights into both system health and patient status. We have implemented distributed tracing capability that provide crucial visibility into patient interaction during network disruption. This allows us to maintain accountability and data integrity despite challenging conditions. Our advanced machine learning algorithms can identify potential system failures and psychological emergency before critical incident occur. Field testing shows our system can detect deterioration up to 13.5 minutes before conventional indicators potential life-saving early warning. Finally, our intelligent bandwidth optimization, prioritization, transmission of life-critical metric when communication infrastructure is severely compromised. This ensures that the most important data get through even when bandwidth is extremely limited. Error budgeting for critical care. We have adopted the site reliability engineering concept of error budgeting to ensure our system maintained appropriate reliability for different functions. For overall system reliability, we have targeted 99.9%, which means a maximum downtime of just 5 minutes per year. This ensures that healthcare providers can depend on the system being available when needed. For critical alert delivery notification that can be life-saving, we aim even higher with 99.999% reliability target. This translates to less than 1 minute of annual downtime for this critical function. For non-critical function, we allow slightly more flexibility with a 98.5% target. The strategic approach allows more innovation in secondary features while maintaining the ironic reliability for the most important capability. This error budgeting approach ensures that we focus our reliable efforts where they matter most, on the function that directly impacts patient safety and costs. Healthcare-specific SLIs and SLOs. We have developed healthcare-specific service-level indicator and service-level objectives that directly relate to clinical outcomes. For vital side latency, we target less than 1 second with a critical threshold of 3 seconds. This ensures that healthcare providers are working with current patient data, not historical information that might no longer reflect patient's data. Alert delivery time is even more stringent, with a target of less than 200 milliseconds and a critical threshold of 2 seconds. When a patient's condition deteriorates, every second counts, and rapid alerts enable fast intervention. Data accuracy targets 99.5% with a critical threshold of 98.5%. This high standard ensures that critical decisions are based on trustworthy information, reducing the risk of treatment errors. Finally, battery life prediction accuracy aims for a ±5% error with a critical threshold of ±10%. Accurate battery prediction prevents unexpected device failure that would leave patient unmonitored during the critical periods. These healthcare-specific metrics ensure that our system meets the unique requirement of medical monitoring in disaster environment. Graceful degradation pattern. When resources become constrained, our system implements sophisticated graceful degradation patterns to maintain essential function. Our priority-based function shedding disables the non-essential feature first as resource termination, preserving critical monitoring functions until absolute failure. This means capabilities like high-resolution wave or historical data access might be reduced before vital signs monitor is updated. Data resolution scaling dynamically adjusts the sampling rate and precision based on patient status. This maintains higher resolution for abnormal reading, ensures critical accuracy when it matters the most, while conserving resources on stable patients. Our local first processing approach shifts to autonomous operation when disconnected from central infrastructure. Local alerting continues without central system, ensuring patients monitoring continues even when the network fails completely. Finally, cross-device redundancy allows nearby devices to assure monitoring reliability for failing unit. Patient data is seamlessly transferred between devices, maintaining continuous monitoring even when individual components fails. Real-world impact. Our system has already demonstrated significant real-world impact across multiple scenarios. During the Nepal earthquake, we successfully monitored over 5,000 patients across 15 makeshift field hospitals with 99.3% uptime during critical disaster response operation. This provides continuity of care despite complete collapsed infrastructure enabling more efficient triage and resource allocation. Following Hurricane Maria, a system was rapidly deployed where hospital infrastructure collapsed, providing 70,000 patient hours of uninterrupted vital monitoring in an extreme condition. This allows healthcare providers to focus on treatment rather than manually monitoring, significantly improving the efficiency of limited medical personnel. Beyond immediate disaster response, our technology has transformed healthcare delivery by extending critical monitoring capabilities to facilitate 200 facilities in underserved regions without reliable power infrastructure. This demonstrates how innovation driven by extreme requirements can broader impact on global healthcare access. Key takeaways. To conclude, I want to emphasize that SRE principles can transform healthcare technology reliability in extreme conditions when human lives depends on uptime. Traditionally reliable standard and approach simply aren't enough. Our research demonstrates that through focus, innovation, and in connection reliance, power optimization, update mechanism, and graceful degradation, we can create health monitoring system that functions reliably even in the most challenging environment. The impact extends beyond immediate disaster response, potentially transforming healthcare delivery in resource-constrained environment worldwide and establishing a new standard for medical device reliability. Thank you for your attendance. I'm happy to take any questions about our research or specific technical approaches that we have done. Thank you again.